Hello everyone. In this video, we'll be talking about the simulation of temperature in primary and secondary shear zone in shaping process. This video is prepared by Kalpesh Rathi, Soumya Singh, Hemant Duntam Sethi, and Himanshu Nima. So let's get started. Since from our prior knowledge, we all know that machining is a process in which a piece of raw material is cut into a desired shape and size by a controlled material removal mechanism. Now, the question which arises in our mind is that why is being heat generated in the machining process? And what is the reason behind the temperature variation? So let us look into it. In plastic deformation of metal machining, most of the energy which is utilized in the cutting process is converted into heat. This heat energy in turn results in an increase in temperature in different zones. Now, what are the different ways in which this heat is being generated? Let us look into it. Now, as we can imagine that when a tool moves over the workpiece, there is a shear zone just ahead of the cutting edge of the tool. That is, when the chip is being removed from the raw material, the deformation of metal is taking place. So, this is one of the reasons of heat generation. Also, when the chip, that is the metal, is physically pulled apart from the workpiece, then heat is also generated at the point of separation. The third reason for the heat generation can be due to the friction between the chip and the rake surface of the tool when the chip surface rubs across or rubs along the rake surface of the tool in case of a continuous chip. Now, having looked upon the different ways in which heat is being generated, we can classify three heat generation zones. The zone 1 is known as the primary deformation zone or the shear zone. In this zone, major part of the energy is converted into heat. Part of this heat generated is carried away by the chip, which results in an increase in the chip temperature. The remaining heat energy is then retained by the workpiece. The zone 2 will be along the chip and the tool interface. This zone is known as the secondary deformation zone. In this zone, heat is generated due to the rubbing of chip against the rake surface. The heat generated in this zone is shared by the chip and the cutting tool. The third zone will be along the tool and the workpiece. This is known as the tertiary deformation zone. It is very intuitive that due to time, the tool will wear down, and so this edge of the tool will not always remain sharp and will get flattened with time. And hence, in this zone, the heat is being generated due to the rubbing between the flattened end of the tool and the finished workpiece. The heat generated in this zone is then shared by the workpiece and the cutting tool. Now, having looked upon different methods of heat generation and the reason behind the temperature variation, we will now look up how to quantify and to simulate this temperature variation in the machining process. We'll now be looking into different methods of simulation of the temperature variation in machining using ANSYS and Abaqus. The first method which we'll be talking about is the arbitrary Lagrangian Eulerian, that is the ALE technique. Now, as we all know that in a Lagrangian analysis, the computational grid deforms with the material, whereas in an Eulerian analysis, the computational grid is fixed in space. The Lagrangian calculation embeds a computational mesh in the material domain and solves for the position of the mesh at discrete points in time. We also concluded from the study of the research paper that the Lagrangian formulation required a criterion for the separation of the undeformed chip from the workpiece. Here, the ALE technique combines the feature of pure Lagrangian analysis and Eulerian analysis. This technique with pure Lagrangian boundaries is applied in the simulation of machining with round edge cutting tools to avoid frequent remeshing for chip separation. That is, the requirement which we were facing in the pure Lagrangian technique is being fulfilled by the ALE model. This technique is very efficient for simulating highly nonlinear problems involving large localized deformations and changing contact conditions, such as those experienced in machining. The second method which we'll be looking up is the adaptive meshing method. This is a method to concentrate the elements to regions with large gradients. Abaqus provides a very general and robust adaptive meshing capability for highly nonlinear problems ranging from quasi-static to high-rate dynamics. That is, whether it be the processes always tend to remain in an internal equilibrium, or be it the processes which are occurring at very high rates, all can be taken care by the adaptive meshing technique. This technique does not alter the elements or the connectivity of the mesh. This technique also allows free boundary conditions, whereby only a small part of the workpiece in the vicinity of the tool tip needs to be modeled. The third method which we'll be looking upon is the element distortion control method. The distortion control is designed to prevent negative element volumes or other excessive distortion from occurring during an analysis. In contrast to the adaptive meshing technique, distortion control does not attempt to maintain a high-quality mesh throughout an analysis. Elements with distortion control cannot be included in an adaptive mesh domain. In the further video, when we'll be talking about the simulations of temperature in Abaqus, we'll be using the element distortion control technique and not the ALE technique. The reason behind doing this is the limited computational power. Now, after looking upon the methods of simulation for the temperature variation, we'll be now talking about the material modeling. The first model into consideration will be the Johnson and Cook constitutive model, that is the JC model. This model is used to consider temperature, strain rate, and hardening effects on the instantaneous value of stress required to continue plastically deforming a material. That is, we'll be evaluating or we'll be looking upon an expression for the flow stress. So the expression is as follows. Sigma, that is the flow stress, equals to A plus B into epsilon to the power n into 1 plus C ln epsilon by epsilon naught into 1 minus T room divided by T melt minus T room to the power m. Here, A is a constant which denotes the initial yield strength of the material at room temperature. Epsilon is the plastic equivalent strain. Epsilon naught is the reference strain rate. This is used to normalize the plastic equivalent strain. Rest, B, N, M are constant which are specific to the material being used. T room is the room temperature, T melt is the melting temperature, and T is the current temperature. A point to be noted here is that when the temperature T is equal to the melting temperature, this term reduces to 1, and this whole expression reduces to 0. So we can say that when the temperature is equal to the melting temperature, it leaves the constitutive model with no temperature effect. This is a very important point which is to be noted here. The second model which we'll be looking upon is the friction modeling. As we can see that we can divide the region of the workpiece into two parts. The first one being the sticking region, that is when x belongs to 0 to LP, it will be the sticking region, and when x belongs to LP to LC, it will be the sliding region. So these are the two different regions in which our tool surface can be divided. So as the sticking region forms across the tool chip contact area near the cutting edge, and the frictional shear stress at the sticking region, that is tau p, becomes equal to the average shear flow stress at the tool chip interface on the chip, that is K chip. So we can say that tau p is equal to K chip here. Now over the remainder of the tool chip contact area, a sliding region is formed, and the frictional shearing stress can be determined by using a coefficient of friction, that is mu. So based on the description provided here, we can say that the shear stress distribution on the tool rake surface can be represented as two distinct regions. The first one being the sticking region, that is when x will belong to 0 to LP. That is in this region shown in the figure, when tau fx is equal to the tau p, which is again equals to K chip. Also here, the mu sigma nx should be greater than or equal to the tau p. That is, in the sticking region, we can say that the frictional shear stress in the sliding region is greater than or equal to the frictional shear stress in the sticking region. Whereas, as part 2, we'll be evaluating the shear stress distribution in the sliding region. That is when X will belong to LP to LC. That is the region which is now shown in the figure. Tau Fx will be equal to mu sigma Nx. And here, the frictional shear stress in the sliding region will be less than that of the sticking region. Now, having looked upon different material models, we can now summarize our follows. The major steps which will involve in our simulation will be the explicit ALE modeling. So here an explicit dynamic ALE modeling approach is used to conduct the FEM simulation of orthogonal cutting considering round tool edge geometry. Second will be adaptive meshing. That is, the chip formation process is simulated via adaptive meshing and the plastic flow of work material in the vicinity of the round edge of the tool. Third will be the CPE for RT quadrilateral elements. That is, both the workpiece and the tool models use 4-node bilinear displacement and temperature quadrilateral elements. That is CPE for RT elements. Also here, we have made an assumption about the plane strain condition. That is, the only non-zero strain components act in one plane. This assumption is made for the deformations occurring during the high-speed orthogonal cutting process. This was all about the simulation methods and the material models. We'll be now looking upon the simulation of temperature variation in ANSYS.
So moving on to ANSYS analysis. So here the tool and workpiece geometry and material assignments are in accordance with paper. Now we'll analyze the results. Coming to the stress analysis. Here we can see that as the tool moves towards workpiece, the stresses are generated and the maximum stresses are found to be in this region. Now we'll move on to the temperature analysis. Running the animation. Here, the maximum temperature is found to be in this region, and it is around 512 degrees Celsius, which is around half of the value that was found out in the paper. So, what are the reasons for this deviation in the temperature that we got? So, one of the reasons is we have in the ANSYS analysis we haven't used friction modeling, and also the adaptive meshing is not used because of the limited computational power. So now we'll move on to abacus analysis, where we have used elemental distortion control method.
This is the FEM analysis done to see the effect of edge roundness on stress and temperature fields in the shaping process. Radius of the tool is 25 micrometers and distance by which the tool advanced is 1 millimeter at a speed of 300 meter per minute. At this high speed, effect of strain rate is significant on flow stresses. So JC model is considered for modeling that material. So elemental distortion control is also used for the analysis. The method used for simulation is element distortion method, which helps to avoid failure of simulation due to high distortion of elements of the mesh due to large compressive and shear deformations in relatively small area, which can lead to negative increment time. The negative increment time has indeed occurred while implementing ALE method by which the simulation has failed. Time increment is chosen by the software in the order of the time taken by the elastic wave of the material to travel through a single FEM element. Mesh quality at a given time matters in deciding this. So EDM improves the mesh quality whereby reducing the error of and simulation time. Better way is to use ALE, but being unable to resolve the error caused by excessive distortion of elements in ALE adaptive meshing, Simulation is performed using EDC, which predicted maximum temperature of 931 degrees Celsius near the tool edge, when compared to the 1329 degrees Celsius by ALA method in the paper. Due to the very low mesh quality generated in EDM, accuracy of the stress predicted by EDM were not as accurate as that of the paper, but it did predict the machine-induced stresses and tertiary shear zone into account.
Hello everyone, my name is Himanshu Nima and I'll be taking it ahead from here. So until now, we've discussed three methods which are ALE, distortion control and adaptive meshing. In this part, we'll be looking at another one of these methods. The method we are going to be discussing is called finite element analysis. And just a heads up, we haven't really performed the simulation using this method, but it's always good to know about what methods are available. So with that in mind, let's dive right into it. The name of the paper that we'll be discussing is Thermomechanical Modeling of Orthogonal Machining Processes by Finite Element Analysis. The paper was written by S. Lee and Y. Shin of Purdue University. First things first, let's talk about what finite element method is. The FEM is a particular numerical method which is used for solving partial differential equations in 2 or 3 space variables. It subdivides a larger system into smaller, simpler parts that are called finite elements, probably where it gets its name from. And this is achieved by a particular space discretization in the space dimensions. This is implemented by the construction of a mesh. Mesh is the numerical domain for the solution which has a finite number of points. The FEM formulation of a boundary value problem finally results in a system of algebraic equations. Talking a bit more on that, the simple equations that model these finite elements are then assembled into a larger system of equations that model the entire problem. In conclusion, the FEM finally uses a variety of methods from calculus to approximate the solution by minimizing an associated error function. Next, let's look at the advantages of FEM. Complex geometries and irregular shapes can be easily modeled in FEM because a variety of finite elements are available for discretization. FEM also allows boundary conditions to be easily incorporated. Different types of material properties can be easily accommodated in modeling from element to element as well as within an element. Next, we talk about the machining model. Here we discuss two types of shear deformation zones. First being the primary zone, which is bounded by OBCAD. Second being the secondary shear deformation zone, which is bounded by ODE. Here we look at some of the common differences between them. First one is just the description of the area. So like I said, OBCAD is the primary one and the ODE is the secondary one. Next, we look at some of the more important ones. In the primary shear zone, microscopic rubbing takes place due to shearing. So in this, there is microscopic rubbing, whereas in the secondary one, there is microscopic rubbing. In the primary zone, most of the heat generation, that is 70 to 90% of the total cutting heat is generated in this area, whereas in the secondary one, only about 10 to 20% of the heat is generated. The cross-sectional area of the primary zone depends on the uncut chip thickness, shear angle, and rake angle, whereas for the secondary zone, it depends on contact length, chip flow velocity, rake angle, and presence of chip breaker, etc. Next, we talk about modeling a workpiece chip separation. First, we talk about the material being used, which is, in our case, 1020 carbon steel. Next, we talk about an important FEM assumption. The width of the cut D is much larger than the uncut chip thickness T1. Basically, when the chip is cut, it has a certain width B, and for our assumption to hold true, we need it to be much larger than 10 times the uncut chip thickness T1. Next, the workpiece is represented by 4-node bilinear displacement and temperature plane strain elements. All right, so next we talk about the master and slave surfaces. So by definition, the surface EF is called as the master surface, while the surface EG is called slave surface. EG is part of the workpiece, while EF is part of the chip. All right, so before the simulation, EF and EG, both their nodes are perfectly bonded. That is, they have equal displacement in all the directions. However, during the simulation, these nodes start to debond, and the debonding follows a certain criteria. The criteria that we have chosen for our simulation is the controlled crack propagation criteria. And the reason for it is that ultimately the material is separated through micro cracks which develop as the tool moves into the workpiece. So the next obvious question is, what exactly is controlled crack propagation? Well, in controlled crack propagation, we first choose a particular crack length versus time relationship, and this is decided on the basis of the movement of the cutting tool. All right, so in our case, like you can see, we've taken a linear relationship, and then after this, we select a reference point on the workpiece material, and as the nodes debond, we calculate the crack length in reference to the reference point. This is plotted against time, and we get a real-time crack length versus time graph. All right, and based on these lengths and the given crack length time, the time increment is adjusted so as to ensure that the debonding. So basically, if it starts to deviate away from the curve, we can adjust the time increment so that it follows and it falls within the prescribed time tolerance for the crack to reach that length. All right, so next we look at the kinematic boundary conditions. Here we see that the surfaces AEL, AB, and BG are assumed to be stationary while the other surfaces are allowed to move freely. Please note that the condition that AEL is stationary is valid only when this length is pretty large. If this length becomes comparable, then the assumption that AEL is stationary is no longer valid. The other assumption that we make is that the friction forces at the tool chip interface are neglected. However, in place of that, a heat flux associated with the friction effect is calculated from machining experiments and applied to this contact area. So now looking at the constitutive equation, we have assumed an elastic viscoplastic material model. In such a model, isotropic strain hardening is assumed, and the stress is given by the following formula. Here, the symbols have the usual meaning, with N being the strain hardening index and M being the strain rate sensitivity, both constants for a particular material. The function F is defined below, where T star is equal to T by Tm, Tm being the melting temperature of the material. All right, so next we talk about finite element formulation. And as mentioned, the displacement finite element method approximates equilibrium requirement in the form of a virtual work statement. And as shown here, we use the conservation of energy to calculate these integrals and then eventually find a stress. And what follows after this is a series of simplifications. They can be derived as there are some matrix manipulations. All these goes on behind the simulation. You don't have to do all this. This all goes behind in the simulation. And finally, we come to the last part, which is the simulation of the orthogonal metal cutting tool. So this formula, this represents the nonlinear temperature displacement solution, and where QPL is the volumetric rate of heat generation. And all these terms, eta is a fraction of mechanical work required for plastic deformation. Sigma is stress, this is the plastic straining. And finally, we solve a steady state two-dimensional form of energy equation to get the solution for orthogonal metal cutting. The way to go about solving this is we try the backward difference method, and then the coupled equations is solved using Newton's method. All right, so all those things go on behind in the simulation, and that brings us to the end of this section. Thank you.